Hello and welcome to lecture 9. Today I want to call out something that we haven't covered yet, which is the optimizer step. So astute viewers might have noticed something that is a little troubling, which is that, we've been doing these joint graphs, right? And typically, as I've talked about, we need the gradients to match the dimensionality of the inputs that require grad. And so if we look at some of these, like for example, MM2 is 2 by 2, but the input at index 0 is 2 by 1, and this doesn't match, right? And then similarly, MM1, which is the gradient with respect to primals 2, is 1 by 2, but the input is actually 2 by 1. So like, what's going on? And so I want to draw your attention to this, right? So at the end of the day, with neural networks, we typically have a parameter, and then these parameters will flow through your graph. And then later on, when you calculate the loss function, you'll calculate the backwards, and gradients will flow back. And gradient is actually accumulated in the parameter. But notice that the gradient is actually separate from the parameters. The parameters are updated relative to the gradient via something like the optimizer step. And so what's interesting is that the DTensor redistributes oftentimes will not happen until the optimizer steps. So if we go back to here, when we're returning these gradients, they're being stored here, and they might actually have a different placement or dimensionality than the actual tensor that requires grad. And it is the optimizer step that will do the redistribution to make sure all of the placements and dimensionality match. So here I've gone ahead and made a simple example. So what we've done is we have our local tensors, but this time we set the required grad on the DTensor to make it a lot clearer to see what's happening. Our compiled function is still just the matmul. And we've also used this thing called debug mode, which is a really nice context manager that allows us to see the underlying DTensor operations that's happening. So basically we construct these two tensors, which serve as our parameters. They're sharded by columns. We invoke our matmul. We get back a DTensor. We call .sum on it to emulate some sort of loss. And then what we do is the following. So first we call loss.backwards with this debug mode. And this will show us all of the operations that are happening in the backwards. This is the part where we're just accumulating gradients into our tensors. And then we do another debug mode where we do an optimizer step. And this is the part where we actually update the parameter weights. And so I've run it here already, and you can see that the backwards, we construct the tangent, we do our matmuls with the transposes, and then we call detach. And what detach is doing is it's effectively adding these tensors to the, it's just accumulating these gradients into this little buffer area. And what's interesting is you can see that what we are detaching is these partial and shard by 0 DTensors, but this does not match our shard by column DTensors, right? And this is where the optimizer step comes in. So once we get to the optimizer step, you can see that the optimizer will basically add the gradients after the optimizer transforms it a little bit to the parameters. And when it does that, that is when the redistribution happens. That's where you see the partial becomes shard 1, and then the shard by row becomes shard by column. Hopefully this kind of demystifies a little bit of what's going on behind the scenes. And in the next few videos, we'll dive further more into the AutoGrad engine to build a better intuition of what's going on.